that's Twitch. Okay, good. It knows I'm streaming now. I'm gonna go ahead and hit reload one more time here. I'm not sure if the internet's actually recovered. It was pretty bad before, but we'll see. I'll tell the world that I'm streaming Procjam. Gonna put cities on planets. And then over here, and paste it in again. And then over here. Oh, that was an interesting sound. For some reason, I am exhausted, so should be okay. We're not doing anything terribly complicated, but whew, I feel tired. I spent about an hour last night doing some work here that I didn't want to just garbage up the stream with. Basically, I put in a new kind of math randomizer, a new kind of noise field. I bought it on the store because the noise field that I was using wasn't really very fast. So I've recreated the moons to largely use that kind of noise field, that noise generator, but it's backwards compatible, so the blue planet and the hot planet both have their old method. I did a couple of optimizations and made it so that you can click on planets to make them glow. But what we're going to do today is make it so that when you click on a planet to make it glow, you actually get a set of pixels, a whole planet's worth, a whole city's worth of pixels. Oh, turn on the camera, that's right. So here you can see it processing through its startup routine. We're going to go ahead and change this a little bit just so that it takes less time, but I think you've got the basic idea. And then if you click, you can put on little dots. And what we're going to do is we're going to make these dots into cities instead of just dots. And what that's going to involve is moving across the texture, looking for differences in height and color. The problem with that is that the texture is not flat. 1 pixel up from this eyeball is not where you think it would be. It's skewed off to one side or the other in the UV coordinate system. So in order to make this work out, we're going to need to have it so that it has a way to determine which pixel it should look at next. And that shouldn't be too hard, but it will involve a little bit of math. The problem is, of course, that we are using math that is not actually correct. So we may have to polish it a little bit later, but for now it should be fine. All right, back down to 0 viewers. That's what I'm here for. So what we're going to need to do is over here on the planet, we're going to close all this random bits. The planet and the clickmaster are what we need. So the planet right now has the ability for us to tell it to set a city pixel at any UV coordinate, but we also need it to be able to tell us what the next UV coordinate is in a direction on the planet's surface. Now for the X coordinate, that's fairly easy. It's just the next along the X axis, but even that's a little bit different because how far we travel depends on how stretched that axis is. Similarly, how far we go up and down is static, but whether we skew left or right is going to be based on how far, how stretched the x-axis is. So in order to make this work, we're going to have to determine how large each pixel is on the x-axis and the offset, the x offset per pixel on the y-axis. Now the thing is, this isn't even like a universal thing because at the top, going up is more skewed and going down is less skewed. So if we look for the neighbors, we're going to need to be able to determine the neighbors and their actual distance. So we're not going to be returning a void. What we're going to need to do is return a vector 3. And that's going to be something that's a little bit odd, but it's easier than any other method I know of. So we're going to go ahead and say get move on planet. And we're going to go ahead and pass it a UV coordinate, and then we're going to go ahead and pass it a direction that we're going to want to move, a delta. And then what we're going to give back is a new UV coordinate and the actual distance moved. So gets us a UV coordinate based on our current UV coordinate moved in real world direction. Now I've got the hiccups. Great. X and Y are UV coordinates. Z is distance from initial. So in order to calculate this, we're going to need to determine what the X stretch factor is. And that's not too bad because we already do it once. The problem is the way we do it before is actually it's iffy because we're doing it wrong. If we take a look, what we're doing is we're calculating out using a multiple of y. So when we get the, where is it? We're looking at planet position here. It might be only in, now that I'm thinking about it, it might not be in here. It might be in the texture proxy. Yeah, it looks like it's in the texture proxy. So let's open up the texture proxy and take a look. All right, here we are. So what we have is this method where we multiply it by 1 minus py times py. That's not actually correct, but it's correct enough for our purposes. I know there is a mathematical function we can use that's technically more accurate, but I couldn't find any implementation that wasn't just freakishly slow. So we're going to be using this same technique. And so 1 minus py times py is going to be our stretch factor. Come on. Cable got skewed here. Hopefully that wasn't loud. So we're going to take a float stretch factor equals 1 minus py times py. Now we don't have any py. Float py equals uv coordinate dot y, but py is actually between -1 and 1 rather than 0 and 1. UV coordinates is between 0 and 1, so what we've got to do is multiply it by 2 and subtract 1. That way we will have a distance from the equator. Y will be a distance from the equator, and that'll work pretty well. And then x, we're going to have to do it the same way. There we go. And there we have the values we need. So what we're going to need to do is these coordinates are in our these are the actual coordinates that we want. So what we've done is we've converted these over into planetary coordinates, and then we found the stretch factor for our UV at the planetary coordinate we're looking at. But the thing is that what we need to do is find the direction that we're looking for. And what that involves is adding that direction to our px and py and seeing what sort of value we come up with. Now I have it passed in just an arbitrary direction value, but the math involved in finding the arbitrary offset is actually fairly complex. So what we're going to do is we're going to create several different functions that just have specialized features. So we're going to go ahead and say move on planet X, and then we're going to have a float X delta. And that's going to be, we are going to move 1 pixel to the left or to the right, and then we're going to return how large that pixel is. So what we're going to want to do here is a uvcoord.x plus equals x delta, but we need to find the distance. So we actually need to vector 3 new UV equals UV I think we have to cast that to a vector 3 because otherwise it'll give us an error, but it's not very critical. New UV.x equals x delta, and new UV.z equals distance to the next pixel much smaller near the caps poles. So in other words, what we're looking for here is a stretch factor is 1 minus py times py. Py times py would be 1 at the poles or 0 at the equator, which means that the stretch factor would be 1 at the equator and 0 at the poles. And that's correct. So we just need to set that equal to the stretch factor and then return it. Move on planet X. Sounds like a 60s sci-fi movie. Move on planet X. And then down here we're going to need move on planet XY, or move on planet Y. And that's going to be the opposite. We're going to want to increase the Y pixel. And then we're also going to need to determine which X coordinate to go to. Now the good thing about moving on planet Y is that we only need to return a vector 2, because the distance is always going to be 1. It's just a matter of what the X offset is going to be. So in order to figure that out, what we're going to need is, the real world distance is going to be 1, but the UV coordinates will drift on the x-axis based on the difference between the stretch factor at the original y value and the stretch factor at the next y value. So we'll do this. py0 equals uv coordinate dot y times 2 minus 1. And then we'll go ahead and say that float py1 equals py0 plus y delta. But the y delta we're using here is going to be divided by the height of our arrangement so that we can go ahead and have it get just the tiniest little chunk. To be honest, well, I guess it's okay. The problem is that there is a chance that the float math will cause an error, and it might be better for us to use an integer-based coordinate system instead of a float-based coordinate system, because it's more chunky and it's not likely to cause any errors. We'll live with this for now. We can change it over to integers later if we need to. So what we need to do is, that is our py0 and our py1. Our px is going to be like that. And the stretch factor is going to have 2 stretch factors. So we'll go ahead and have a stretch factor 0 at py0 and a stretch factor 1 at py1. And what we're going to need to do is determine the new x based on the stretch factors, the difference in the stretch factors. Now, I don't actually know what the difference in the stretch factors would be, but we can go ahead and set the y value correctly. Except for we have to put it back into UV coordinates, which means that we're going to divide it by 2. And then the x value is going to be the same x value that we started with, except that we're going to need to offset it by a certain amount based on the drift. And I don't actually know what the factor is here. It might be raw, or it might be multiplied or divided by width. My brain can't really picture it, but we'll go ahead and do it like that, and we'll know pretty quick whether or not there's a problem. So here in ClickMaster, what we're going to need to do is we're going to need to have a method of determining how far we're going to go with these objects. Later on, we're going to make those into a game objects, a new kind of script. But for now, we're just going to go ahead and hard code it. So right here, we have this set pixel stuff. We're going to go and create a new public void set direction, set ray. Vector2 UV start, vector2 UV. I'll go ahead and make it just similar, set ray x and set ray y. So float delta x, and a float range. And then we're just going to go ahead and get that texture coordinate. And we're going to pass it 1 and 10. So in here what we're going to do is we're going to say while range is greater than 0, do this. So in order to get this to happen correctly, we're going to do the p dot... Oh, there's no p. No p. Elboetch says, "Hi, Craig." Hello. You are the first visitor as far as I know. So we're making cities, and what we're going to do is we're going to find that offset, move on planet X, UV coordinate, and delta X. Now in this case we know that the range is always going to be 1, just because... no, wait, sorry, that's wrong. Vector 3 result equals... So this one actually returns a vector 3 with the range minus equals result.z is what we're going to do. So we're going to go ahead and do a debug.log clicked and then the result. According to the viewer list, there are 4 people, including him, watching, although I'm not sure I can rely on Twitch for that. I have no idea. I don't really consider people who are completely silent as viewers, just because I can't tell whether or not they're real or what's going on. Nothing against you silent types, but you know. Anyway, we're going to pass it in a vector 2 version of result. And we're not going to use color.white. We're going to use color.gray. In fact, we're going to define that color. Color32 color equals new color 32. 128, 128, 128, 128. And we're going to go ahead and suppress it for all of them except for the very last one, which we'll put down here. Although in order to do that, we're going to have to take result and put it outside. Now, that does mean we'll be writing twice, but that's fine. I don't really care. This is just for testing purposes at this point. Uncompetitive says, "Hi there." So we're going to go ahead and see whether this works. Now, what did I misspell? Use of unassigned variable result. All right, so I just cleared a warning, unfortunately, but that's fine. So here we have the really, really low poly planet that we're planning on using just for testing purposes. And let's go ahead and see what happens. Boom. So you can see what we got here is a clicked 1.601. 1 is what I expected to see because this is pretty close to the equator. You see this is 0.9, 0.8. So we got the distance working correctly, but unfortunately it doesn't appear to actually be offsetting. And the reason for that is because I forgot to move our UV start. So you can see here, UV start.x equals result.x. Down here we can go ahead and use UV start. There we go. Which means that we can take result back into here. Perfect. So now we should have it right quite a few times. Boop. That's not the x-axis. That's the y-axis. Interesting. That is not at all what I expected to see. Let's go ahead and turn the camera off and take a closer look here. So the problem with just moving straight up the axis is that it's going to end up skewing when you're near the poles. So if I click here, for example, or here, you can see that those lines, they not only get narrower, well, actually, they do streak straight towards the pole. It's probably because I'm facing the front side of the planet. If I rotate it, I bet it'll. So if I rotate it and then click, By the way, the reason everything is drowned out is because there's a bug in Unity's processing. Uncompetitive cut off his finger, and that's why he couldn't talk until now. Rekton says he only watches, and it's hard to see him writing there. Yep, that's the problem. I'm sure that all of you guys are fairly nice people, but since I never talk to you, I don't really have you in my brain, you know? So this should be X offset, but it's clearly Y offset. What really mystifies me is that it appears to be correct. This is super weird. It may be that I got X and Y backwards, just visually. Maybe this whole planet's been rotated and I didn't realize it. Well, the good news is it appears to be working. The bad news is what we're going to need to do is we're actually going to have this be here. Color 32.white. So what we're going to do is we're just going to go ahead and set array in all 4 directions. And we're obviously going to switch out ray X for ray Y, which we don't have yet, so we'll just go ahead and build it. So when we set it on ray Y, what we're going to need to do is move it on the other coordinate. So here's our delta Y. Now ray Y is guaranteed to be 1 length. So rather than range equals blah, 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 it's just going to be range minus minus. Guaranteed length 1. But the question here is that we need to have this be UV start equals move on planet X, Y. UV start dot delta Y. Right, so that should all work. Now the problem I have with all of this is very simple. It's going the wrong direction, and I don't know what's going up with that. That shouldn't be something that happens. Still, we'll go ahead and take a look. So you can see that what we've got is not what I expected. With one click, we've laid down pieces of planet all over. So these rays that we've got here don't make any sense. That's fascinating. So clearly there's something that's not working out because we're moving only on the y-axis except for one little step on the x-axis, which is quite strange. If I click up there, we get an index out of range. So the index out of range I eventually expected because what we've got is this set city pixel gets us an unwrapped pixel, but we have a wrappable pixel that we can get. Which we'll use. And that will be guaranteed to be valid. It'll also wrap straight across the hidden seam on the planet. If you got it to rotate, you would know what the axis of rotation mapped to. Well, I'm not actually sure what's going on, but I have a feeling this might be related to it. So if we move on planet Y, okay, so that might matter, but it doesn't matter right now. So basically what I want to do here is when I move on planet X, the UVX changes and the UVY remains the same. When I move on planet Y, the UVY changes and the X value, but I don't know whether this is because it's a float math issue and I should be using integer values, because I can do that if I need to. I might have to because I don't. This is like really weird and nonsensical. Yeah, this is very strange. So you have to remember that each of these is made out of 4 different calls to 4 different parameters. And strangely, they don't seem to actually be doing anything. That's fascinating. Okay, well we're gonna go ahead and switch over into indexes. So in order to do that, integer values rather. So in order to do that, we're gonna need a duplicate of this, which is for indexes. And it looks like I'm duplicating code, but I'm actually not. I'm going to be cleaning up a lot of this. So we're going to do that. And then here, we're going to go ahead and just do this. There we go. And that way we can pass it X and Y coordinates. And down here, move on planet X and move on planet Y. We're going to rebuild these to use integer values. The only uncompetitive says he's watching on an iPad, so it's hard for him to say anything. Well, you know, typing on an iPad with a bloody finger, it doesn't sound too much fun. So what we have for a problem is that we can't easily write out, we can't return a double integer and a float. So what we're going to do is we're going to make this a float, move on planet X. We're going to pass it in int x, int y, but these are going to be references, so that when we change them, they change in the other scope as well. Return moves along the x-axis in UV space. Returns the distance between the old and new location on planet X. What we're going to want to have here is that instead of this being a delta, we'll make it an int. So the idea here is that X is going to go ahead and modify itself by that much. But what we need to do is we need to determine the stretch values. And in order to do that, we're going to have to convert the Y value into a float, because we have to do some math that's not going to be integer friendly. So we'll go ahead and say that float y equals float y divided by float width, and then we'll say dy equals dy time plus 1 divided by 2 times 2 minus, so it's dy times 2 minus 1. And that will be a negative 1 to 1, just like everywhere else. And then we're going to go ahead and say that dy equals 1 minus dy times dy. That's going to be the stretch factor involved, and that's going to be what we return. So that's going to be 1 at the equator, and it's going to be 0 at the very, very tippy top. If it is 0, we're going to want to make sure that it is not. So if dy equals 0, then dy equals 10. Just for safety's sake. Don't kibitz on the poles. So that should work. And now we need the other one. We don't even need to have a float there because it's guaranteed to be size 1. Move on planet Y. Ref int x, ref int y, int delta. So we'll have a y plus equals delta here, but we need to calculate out this stuff before we change the y and after we change the y. Typity type, 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 type. So if we do this, then what we're going to need to do is offset the x value by the delta between the two. But it might not be correct. I might have to scale it. We will find out. mathf.abst, no, yeah, mathf.round to int. That might work. We're going to go ahead and kill these guys off because they are pretty much useless. So we're going to go down here into click master. What we do is we get this set ray X and this set ray Y, which pass in a UV start. We're going to transform that UV start into an X and a Y value. So UV start dot X times P dot width and int Y, come on, equals UV start dot Y times P dot height. And then we'll pass in X and Y. And then here will be range minus equals that. And then when we set the city pixel, we'll set the city pixel using the same X and Y, like so. It's a fairly compact way to do things. It works pretty well. We'll do the same thing here. And we're going to go in here in range. We're going to do the same thing, X and Y, except there's no UV start. It's just like this. And then we set the pixel, X and Y. And I think that that's correct, but I'm not 100% sure. Let's find out. Oh, look at all those barfs. Now this float to int cast is going to be an issue, so argument number 3 cannot change from so this is supposed to be an int. That's fine. Anything else? Nope, seems like we're clear. So we'll go ahead and hit play. That code looks a lot better, says uncompetitive. Yeah, sometimes it takes a couple of tries. You know how it works. All right, so what we've got here is a planet that has a couple of forks. You can see that these are correct-ish. For some reason, this is offset by 1 pixel. But it only goes in 2 directions rather than in 4. So that's kind of interesting. It should move in 4 directions because we're using negative deltas. Or not. I'm an idiot. I am an idiot. So there's the problem. I set the range to -10, not the delta. Durr. Uncompetitive says that he's reading it with he's reading an iPad Pro. Okay, so I can actually zoom in on the. I keep forgetting to do this. There's no problem with me zooming in on the code. So if you've noticed that I've forgotten to zoom in on the code, feel free to tell me. You don't need to use spyglasses to figure it out. So you can see that what we've got now is a 4-way split that's nicely framed around the center point. And that's exactly what we want. Now the question is how well it'll work when we are up at the top, or down at the bottom, or off to the side. Let's take a look. Well, that looks right. You can see there are cases where it does have a small off by 1 bug, which we may have to try and fix. But it looks right aside from the off by 1 bug. If I were to spin this planet around, whee, and try it on the backside, turn on the camera. Yeah, that looks pretty good. I don't see any serious problems with this at all. Great. So the last thing we need to do is figure out why it is offsetting funny. And the reason it's offsetting funny is because here, when we set our texture coordinate, we're passing it to the set city pixel directly. And here we're using round to int, and on set city pixel, we're not. So we've got 2 set city pixels. We've got 1 set city pixel that takes in a float, or rather a vector 2, and another that takes in an XY. See? This uses floor to int rather than round to int. So we'll just switch it out so it's the same in both places. And now whenever we click, it should click correctly. We shouldn't have to worry about that. And apparently uncompetitive is going to play Beyond Good and Evil. That is quite a fun game. I have played that many times. So here we can see what it looks like off the top of our heads. Now we've got some issues with this. The first is that the gray we're using is really bright, but that's something that we'll fix later on. And the second issue is that this isn't forking or anything. And the third issue is that the X and the Y coordinates are much too different. In planet space, X coordinates are twice as many as Y coordinates, so we want to use half as many so that we don't have a weird split. Yeah, it's not quite twice, I guess, but the point is, I guess it doesn't really matter because we're going to be just doing a growing algorithm, but it should be fun to do it like either way, I guess. It's time for us to create the landing element, the city module that we're going to be using. So that's a new script. First off, let's go ahead and create a new folder, which we're going to call the planet folder. We'll drop all this crap into it. Boom. And then here what we'll do is we'll create a new script, which we will call a city. All right, so here in the city, this is going to be an object that lands on a planet and decorates it while keeping track of height and color. So to do this, we're going to need to take in a planet, and we're going to need to take in a position. And we'll add in the monitoring in a bit, but for now what we'll need to do is just have this be able to get kicked off. So public void run p initial landing spot, planet, and vector2 landing spot. We'll go ahead and calculate it out. We'll need to have a int size or a float size. We'll go ahead and make it a float size. Public float size equals 10. So p equals planet, landing spot equals initial landing spot equals landing spot. And what we're going to need to do is we're going to need to compute. Uncompetitive says that I misunderstood him. He meant that it reminded me of an impressive demo we saw of Beyond Good and Evil 2, which had a planet with a procedurally generated city. Oh, this is like small potatoes compared to the monkey ape demo that they gave out, the what they call it, you know, the monkey god from Chinese mythology that they're clearly referencing. Also a Dragon Ball character. I can't remember his name for some reason. Anyway, that has some impressive tech behind it. I'm not sold on it as a game, but the tech was really great. And this is very primitive. This is game jam tech, so it's not going to match that. So what we're going to need to do is run a thread. So we're going to do the same thing we did before. We're going to run threads. And the difference is that this time what we're going to need to do is have those threads. Clickmaster can be in the basic scripts. Ganesh statue of an elephant. Well, I mean, there was one, but the main character was a monkey god character. So what we're going to do is we're going to move these guys down into the city. And then here in Clickmaster, what we're going to do is we're just going to have that element. So public city, city. Later on, we'll fix that up to be a little bit more interesting. So city dot run planet and hit dot text record. And then in here, we'll just go ahead and have that be the thing that gets a run. And our landing spot will replace these. Except for one small difference, we don't have to pass it the planet because we have saved the planet. So we'll go ahead and take that out of the equation. So right now what we've got is a situation where we're using set ray X and set ray Y. Those rays will end up forking. So that's what we're going to end up needing to do in the long run. But for now, I just want to make sure this works, you know? So we're going to need to have a city here. Just drop it into the same spot and then drop it on. And take a look at the console. Nothing. So what's this? Okay, so apparently it no longer exists. That's fine then. Hit play, and there's our planet, and we click. Oh, good, it still works. So this is great. It means that we'll be able to figure out exactly what we're trying to do. What we're going to want to do here when we set the ray is that every single one of these times when we pass a value, we're actually going to want to compare the UV values of this new spot so that if they are too different, we can stop or split. So to do that, we're going to need to have an enum. So public enum city ray behavior. I guess I'll use a U because they do, but it's whatever. Normal, stop, fork. So we're going to need to come up with a method of comparing city ray behavior to coordinates. So compare coord. And so to do that, we're going to have the initial coordinates and the new coordinates. So int new x, int new y. Now, one of the issues we've got here is that the original value is saved as a vector2. Initial x and initial y will be saved as separate entities. We'll do that right here at the beginning. Landing spot and landing spot. That way we want to recalculate them every single frame. Elbow just says, isn't behavior British English? Yeah, it's not correct for their own internal standards. This is the only place they use British English, but it's better to be consistent in inconsistency rather than have an inconsistent inconsistency. So what we need is a set of color 32s. So we're going to need to have a height and a couple of other values. We're not going to need the height for everything. The height we can just get as a byte. So h0 equals, and we're going to want to grab from the planet the index. The repeating index, what was it called? Was that was on the planet, or was that on the? That might have been on something else. Let's go ahead and open up the values here. Here's the planet. No, that's a height remapper. Here's the planet. Thank you. And we have a wrappable location index, and it's supposed to be public, not protected. So we'll grab this wrappable location index. So int index1, index0 equals planet.wrappable location index. That's something else we can cache. In fact, we can cache all this stuff. So we'll go ahead and just do that. We'll cache it all. We'll cache everything. Protected int initial x, initial y, initial index. And then initial height, protected color 32 initial albedo. And so we'll just go ahead and calculate those right away. Initial height initial index equals planet.wrappable location index initial x and initial y. Initial height equals planet dot albedo equals metallic pixels. Initial index. Hurry04 says it's nice that someone else besides him is using monodevelop. Yeah. I don't like Microsoft products because they require you to be logged into Microsoft servers, and I don't really care for that. And then we only need one of these values, and it's green. And then we're going to want the initial color. equal to planet.albedo initial index. There we go. And then down here, what we're going to do is we're going to grab all of the values, all of the new values, and it's going to be new x, new y, and then we're going to go ahead and say that int height equals p dot height pixels. No, it's p dot metallicity pixels index dot g. We use the metallicity on both places. Yeah, okay, good. I couldn't remember for a second. And we're going to color 32 albedo equals p.albedo index.g. Index, just there. That's it. So this is going to be a set of parameters that we're going to need. Albert says, why is the height in the metallicity pixels? So the actual height map stores normal map information, which all 4 channels are required to be something specific. So rather than trying to figure out what the height on the planet is based on the normal map, we're going to be using metallicity.g, which just stores the absolute height of the planet at that particular location. Because the height map is actually a normal map, and I probably should rename it. So the last thing we're going to do is we're going to compare the height. So height minus equals, and then the Elbowitch says, why would the normal map use 4 channels? You'd have to ask Unity. So, well, I can rename it right now while our brains are on it. So up here, height map. See, the problem is it is a height map while the planet is processing. It just turns into a normal map at the very end. Still. All right, should be fine. Right, so here's the city. We're getting the albedo. We need to get the difference between the height and the original height. And we'll go ahead and make that a value that we can tweak. So public int max rise equals 5. If mathf, can I do it with an integer? Integer, no. So if mathf.absolute value height is greater than or equal to greater than max rise, then return stop, right? What is the city ray behavior? If height equals 0, if that's exactly the same height, then return city ray behavior normal. Otherwise, return city ray behavior fork. The only problem is that we are doing something a little bit unusual. We'll have to take that into account because we don't actually want to fork every single time it tells us to fork. We'll go ahead and figure that out in a moment here. So what we've got is a set ray y and the set ray. These here get the compare coordinate, right? So we're going to want to grab that coordinate. City ray behavior, CRB, equals compare coordinate, x and y. Same down here. And then we're going to want to figure out exactly what we're doing. Bool forked last round equals false. And then here, forked last round. We'll do a switch. CRB. Case city ray behavior stop, return. Case city ray. Okay, well, actually, we're not going to want to return. We're going to want to paint it as a brighter color. So we're going to have 2 colors here in order to have this city really, really seem good. These values are up on top. These can be protected. Public color 32, run color, and city color. What do you want to call it? Settlement color and road color? Block color and road color? Block color, road color. And then here we'll do block color, or road color rather. Road color down here as well. It's actually going to be, sorry, I'm thinking too fast, doing things a little bit out of order here. This is going to be block color. And then down here we got the same issue. Well, we'll go ahead and actually paste it in because it'll be the exact same code. But here you can see we're passing it white. We're going to want to pass it block color. And that should all work. And this color can go away. Don't need it. Case city array behavior normal. Do that with the road color. And the last thing we're going to have is for the fork. Now the fork is definitely the most interesting of our possibilities. If forked last round, then we just go ahead and we don't want to return, we just want to break. We just go ahead and do this. So if we forked last round, don't fork again. Otherwise, forked last round equals true. And we're going to go ahead and ask for it to continue. Now the reason we're going to ask for it to continue rather than break is because right here we're going to have a forked last round equals false. And we don't want that to trigger, see? So if we're forking now, what we're going to want to do is we're going to want to go ahead and set the block color. And then we're going to want to randomly do a set ray y, either up or down, and have that work out. So the only problem we've got at the moment is that we don't have any XY set rays. And we're going to go ahead and convert right now into having an XY set ray. Public void set ray x, int y, int delta x, float range. Set ray x, y, delta x, range. And we're going to do the exact same thing with ray y. Public void set ray y, int x, int y, int delta y, float range. Set ray y, x, y, delta y, range. And that way we'll be able to do this without having any problems with float math conversions, because we'll just stay in integer values for the rest of the process. So when we try to fork it, what we're going to need to do is fork it on setting the ray on a y-axis rather than on an x-axis. And we'll pass it in our current x, our current y, and our delta y, but we don't know what that is yet. It's going to be either -1 or 1. We'll go ahead and say 1 for the moment. And then the range. So we're gonna go ahead and say if random.value is less than 0.5, then do it this way, otherwise do it the other way. Very, very basic setup. So that works out, and then we continue, and that skips the fork last round turning off, and that just makes sure we don't have two forks in a row when we have like a pixel gap between them. So we're actually going to change fork last round now that I'm thinking about it. We're just going to make it forked, and we're going to skip every other fork rather than having it, do something. So if forked and CRB equals city array behavior fork, forked equals false, CRB equals city array behavior dot normal. That's an easier way for us to do this. So in that case, what we've got is a set of situations where we fork and we do a whole bunch of other stuff, and it should all work out. All we need to do is duplicate all of this stuff for our y values. It's almost identical code, but not quite close enough to actually, use, unfortunately. So if we set the array y, we got forked here. City array behavior. Set pixels, not needed. Forked. Yep, here we are. And this is set array x. Right. Let's see how many errors I have. Boom, ba-doom, boom, boom. Cannot imply indexing with expression of... just spelled a couple of things wrong. Was that the extent of it? That was. The variable albedo is assigned but never used. We'll go ahead and use it later, but for now we'll just comment it out because I want to see if this works. We have to change the city a little bit because it's got black as its glow-in-the-dark color, which is a little bit... So we'll just change it to this kind of very, very faint gray. Now we have a planet, and if we click, it's very, very bright. Even though I made them quite dull gray, it's apparently still too bright for our needs. I can always degrade them even further. But here you can see the result. This result is very dense. It might be too dense. We might want to make it so that forked is a little bit less aggressive. So we'll go ahead and make this an integer value. Int forked equals 0. And here we'll say if forked is greater than 0 and then we'll go ahead and so if forked is greater than 0. Oh, I just hit tab, didn't I? Okay, well, we'll start here because we need to do both anyway. Int forked equals 0. If forked is greater than 0, forked minus minus. If CRB equals fork, then do that. And down here, we'll do the same thing. And the difference here is that when we say forked, we're not going to say forked equals true. We're going to say forked equals 5. Alboy just says, a bit much road. Well, I want a lot of road, so, All right, now that looks more like what I have in mind. The only problem is that this guy down here didn't get any forks at all. It was on perfectly flat ground, so he never forked. What happens if I just return fork instead of normal all the time? Wow, that's dense. Uncompetitive says it's coming along nicely. Yep, the only problem I've got is that if I don't fork, it ends up really, really bland sometimes. But maybe that's what I want. Maybe it's like, yeah, you picked a bad spot for your city. But you can see that basically what we're going to do is we're going to click and it's going to build a city. And then what's going to happen is people are going to bid on the city. So the other thing I want to do is right now, range is on a per unit basis. Like every array has its own range. I'm actually going to want to have that be something that actually gets depleted in a different way. The problem is that each of these is a depth-first situation, so there's no counter for arrays that expire. What I guess I'll do is when you fork, I will reduce your value. And what I'll probably have to do now is really increase the range of these planet objects, which is fine. This is more or less what I want it to look like, except for we're running at such a small size that you can't really see what it's supposed to look like. So we'll go ahead and just modify the scene a little bit until we can see the whole thing. And then we'll go ahead and give it a shot at full size. This is oddly dark. Huh. Oh, the normal map was all screwed up. That's fine. We'll deal with that later. So this is what it looks like at full scale, right? And if you're trying to pick a place for a planet, you might be like, how about right here? And you'll get a little city, right? Or how about here? And you'll get a little city. How about here? Little city. The problem is that these are quite small, but these are supposed to be the starting cities, so they're supposed to be quite small. You can see that most of the time you don't get that nasty glow. So the idea here is that it's only going to glow if you put your cities in the right spot, or if they are so dense and bright that they cause it to glow. Either way, it looks like the roads need to be a little bit more smaller. So we're going to go ahead and do that. This road color is currently a dark gray. I think what we're going to do is bring it down even further and make it blue instead. So we'll just raise up the blue a little bit. No, because blue is a naturally occurring color. We're actually going to raise up the green a little bit. Only a few planets have green, and we're going to have cities based on planet type. So maybe it'll be red for this kind of planet. I haven't really decided. So what'll happen is while this is phasing in, there'll be some talking heads over here commenting on the nature of the planet. And that's kind of the point. You're going to have some conversation distracting you from the slow process. Yeah, that seems more or less how I want the starting cities to look. Let's go ahead and take a look at how a more advanced city would look. Well, these don't actually have too much better. Well, they're noticeably better, but they're not so much noticeably better. That should be okay, I guess. It's weird how small that value is. I know what's happening. I'm an idiot. There we go. That should be better. Right. And I think the rise of 5 is probably a little too small. Let's go ahead and go with a 20 and a 10. Because this rise is out of 255. So when I click, boom, 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 shaboom. Wow, that's really dense. Boom and kaboom, shaboom, boom. All right, so we've got a good diversity of cities that get built. And sometimes you'll hit the jackpot and sometimes you will not. And the point is that you're going to want to get a feel for what's a good and what's a bad spot. Now, when it comes to calculating these cities in terms of what people want, there are a few values that matter. Some of them are global, like how far from the equator it is or how far the planet is from the sun. But some of them are going to be things that are specifically related to the albedo. Like if you see blue, that's water. And there are some people who are going to like water cities and some people who don't. And if they are surrounded by rises, if the city ends on a whole bunch of rises, then they're in a crater. And if it ends on falls, then they're on top of a hill. And if it ends on rises and falls, then they're in a corner. And those all have values as well. So that's going to be how we are going to have this work in the long run. For now, however, I'm going to go ahead and randomize the planet and start again, because I'm tired of looking at ocean. That's still mostly ocean, guys. Let's spin it. Yeah, spin. So here we can see some desert, and if I click on the desert, I get a little city in the desert. This city is much, much denser than I need. Let's go ahead and recalculate. And while we're recalculating, we'll go over to the main camera and adjust the settings a little bit, because 20 is obviously not 201, definitely not 2010. There we are. 20 was a very, very big set of cities. All right. So now we can put down cities and we can see how they look. And you can see that depending on how you place them, you get different results. Gonna go ahead and take a screenshot of that. I guess it doesn't look very impressive at the moment, does it? Well, anyway, what we need to program in now is a set of concerns for the city's counter. It needs to count when it's told to stop, and it's going to want to count which direction those rises and falls are. So to do that, we're going to create a list, protected list int, I guess it's a dictionary, isn't it? And we can just do it with 3 ints. Int rises, int falls, int ends. Why am I doing ints, ints, ints? Rises, falls, and completes. And then in here, we'll go ahead and set that up. Rises equals 0, falls equals 0, completes equals 0. And then down here, we're going to want to have this be a bunch of stuff. So when we have a city behavior stop, we're going to want this to add to either rises or falls. If height is greater than max rise, then rises plus plus. Else falls plus plus. Up here, if we do all of this stuff and we actually run out of range, and we reach down here and our range is now 0, if range equals 0, as less than or equal to 0, then complete plus plus. Now, when we've completed all of this stuff, we will know what sort of result happened. So we'll go ahead and say calculate result. And we'll say public void calculate result. And we'll go ahead and take a look. So we'll say if completes is greater than mathf.max rises and falls, debug.log city is on a flat plane. Else if rises is greater than falls times 2, debug.log city is in a crater. Else if rises is, falls is greater than rises times 2. Debug.log city is on a ridge. Else debug.log city is on a hillside. We're going to go ahead and make some enums for that. So public enum city emplacement. Unknown flat crater ridge side or hillside. And we'll go ahead and make that a public value. Public city emplacement. And we'll go ahead and put that in here. Emplacement equals city emplacement dot flat dot crater dot ridge dot hillside. No, nothing named false. Maybe that's because I spell shit wrong all the damn time. There we are. So now let's try this one more time, this time with the knowledge of exactly what kind of cities we're going to be creating. Boink. And zoink. All right. So now if I click somewhere, I should be able to, hold on, let's just go ahead and turn the planet till I have a good view of some land. Here's some land. I should be able to determine, before I even click, I should know what I'm going to get. So if I click in here, I should get that I'm in a crater. Let's go ahead and find out. The city is on a hillside. Well, that's actually true because I didn't get across the crater. If I click in here, city is in a crater. Yes, that's right. Let's uncollapse. And then down here, I should get that it's on a plane, but I might get it's on a ridge. City's on a flat plane. Good. And in here, it should be a flat plane unless I'm unlucky, at which point it should be a crater. Flat plane. If I want a hillside, I could try here. It's on a flat plane, so that hill doesn't count as hilly enough. These all count as flat plains. It's on a ridge. See if I can get another ridge. Will this count as on a ridge? Hillside. Hillside. Flat plane. So we can tell a large amount. We're going to probably need to customize these values some. Let's go ahead and put a debug in here. Debug.log complete rise fall plus completes plus rises plus falls. Wow, that's a really squeaky mouse I've got today. All right, so here we have our little planet. We're going to spin it around again just because it's not in a great position for us at the moment. All right, there we go. And then when we click on it, we should be able to get a lot more information about what's going on based on the values that we're seeing. So if I click here, you can see that what we've got is nothing cleared. We had 6 rises and 3 falls, which means that we actually did click on a hillside. If we click on it down here, we had 408 completes, 76 rises, and 39 falls. If we move to over here, city is on a ridge. That one worked. And here, city's on a ridge. Yeah, okay. So it might need like a little teeny bit of balance tweaking, but the basic idea is pretty clearly working. Here's a hillside, another hillside. Yeah, click in here, we got a flat plane. Yeah, so the basic idea is clearly sound. I'll go ahead and take a screenshot of that. You can place cities, and the system knows what sort of terrain you've put the city on. Procjam. Let's go ahead and try it with a different one of the planets. That's Earth-like. Let's go ahead and see what it's like with a moon-like. So the moon-like, we can probably adjust it to be the right size. 1, 1, 1, 1. Move it away a little bit because it's a little large. Hit play. Oh, that didn't work. I think the problem is that it's marked as finished. I think I'm going to try and rotate this light so that I get more shadow. Yeah, like this. That way I can place some cities down here and we should get some good results. Oh, there's no mesh collider. Oh, it did not like me trying to do a mesh collider. Darn it. Not mesh filter. Mesh collider. I added it to the directional light. That was why it didn't work. Well, let's go ahead and change the directional light a little bit so we can... I can't even see what's going on. Let's turn off the main camera so we can see what's going on. And then we'll change the directional light a little bit. Yeah, that's actually probably pretty good. And the moon-like needs a mesh collider. Boom. I've got to turn the camera back on. Doop. Well, that directional light isn't really as well positioned as I thought it was going to be. That'll work. Let's go ahead and place some cities. Click, clickety, clickety, click. It's hard to place them on the dark side because I can't see any flat areas. Of course, placing them on flat areas isn't necessarily what you want to do. Okay, now let's go ahead and try it with the fiery planet. Ah, so bright. Let's change that direction of light again, because again, it's not in a very good spot for our purposes. And then we'll start to put some cities down. This is a pretty flat planet. Oh, that was not what I wanted to do. I may need to have some kind of auto split as well. We'll have to deal with that too. I know how to do that, so let's go do that right now before I get distracted. When we're in the city and we have this forked value, what we're going to do is we're going to have it so that forked is always subtract by 1. So if forked is greater than 0 and we are forking, then we're doing normal behavior. If forked is less than -5 and CRB equals city ray behavior normal, and city ray behavior equals forked. Ditto for this. That way we will never go too far away from having the ideal amount of forking, whether or not we're on a terribly flat planet or not. Boom. Bright. Well, I can see that 5 is... Well, no, that's about right. This must be bumpy over here. I just can't see it. And if I drop it onto lava, well, it works, but I might have some rules about cities on lava, you know? I think that 5 is apparently too regular. What we're going to go ahead and do here is make it so that rather than city, you know, forked is less than -5, we're going to go ahead and say if forked is less than mathf random dot range -10 comma -3. All right, now if we click, that's in place where it's not there. That's a little better. So you can see that now our cities don't look super regular. They just look kind of regular, and that's good. That's what we'd like. To be honest, I may be better off just passing in normals for everything. Let's go ahead and find out. Ah, so bright. So the only problem with that is that we get these really, really small cities if you plant them wrong, but that's kind of the point. Yeah, to be honest, I think I like it better like this without any sort of bump forking. I thought the bump forking was going to work out. It does not. All right. So that's pretty cool. You can now place cities. This has been going on for an hour and a half, and that's long enough for me. I doubt I'll stream anymore today, but I'll definitely stream tomorrow. What we're going to do tomorrow is we're going to set it up so that it determines the colors that are involved and calculates out other values, such as how much sun it's going to get and how easy it is going to be to launch crap into space and stuff like that. That's all going to depend on planet types, but we'll get there. That's for tomorrow. For today, that's all that we're going to be doing. I hope you had a fun time, and see ya around. I'm kind of hungry for some reason. Bye.